So specs for the circuit was we wanted to design it where we wanted a 5 volt, uh, 5 volt, 5.1 volt, and that's VG, right? Plus or minus 5%. And we chose a 2N4733A. With the A specifies 5%. If it don't have the A, it's plus or minus 10%. We wanted to regulate with an input voltage coming in between 6 volts and 7 volts. DC. And we needed it to handle a load current between 2.5 milliamps, 7 milliamps. We calculated, and we keep making the same mistake. Unfortunately, I do too. So, first thing we need to do to make sure we get this, we calculate VRS minimum. We'll do this to solve for the resistor. VRS maximum, we'll use it to solve for the power rating of the Zen. A voltage drop would be calculated would be 6 minus 5.1, which gives us 0.9. And VRS maximum would be equal to 7 volts minus 7.1. Minus 5.1. Oh, 1N. Y'all take transistors. Thank you. I was just seeing if I was going to make attention. So transistors start at 2N. Diodes start at 1N. And this gives us what, 1.9 volts? Okay, so we're going to use this to calculate the resistor power. And we'll use this to calculate the resistor size. So we come up here and we said, okay, the size of the resistor, calculated, not chose. RS, in fact, I'll put CAL, so this is calculated. Because this is the resistor we're not going to use. We won't use this resistor. We'll use one that we pick, right? This is going to be the minimum voltage that it'll drop, which is 0.9, divided by the maximum current, which is 7 milli, plus IZK, I think is 1 milli for this one. Which it came up, I think it came up and gave us like 112 ohms or something. So then we always round down. So the next one down, I think, was 100 ohms. And then we multiplied that by 1.05 to increase it by 5%. And if it comes up to be less than 112, that means we're okay. So it comes up to be 111 or something like that, right? So we're okay. So that was our design. So what you have to understand in the circuit, what's actually happening is we're hooking this to unregulated DC, and our unregulated DC is doing this. And of course, this right here would be 7 volts, and this right here would be 6 volts. But it's hard to get that, right? You understand? So, and this would come into our regulated power supply. So we would start off with a transformer, and I'm going to use a halfway bridge because it's easier. I'm going to use a full-way center tap because it's easier to draw. And so we'd come off here, which gives us pulsating DC. Then we would come over here and we'd put a capacitor. And then we'd come over here, and this would be our series resistor. And this right here would be our Zener. Put in there reverse biased, right? And this out here would be our load that's going to require And I don't know what it is. It's going to require 2.5 milliamps through 7 milliamps. Now, the problem is before I hook up the circuit, I want to verify my circuit. So instead of depending on this unregulated DC, I'm going to come up and I'm going to use a DC power supply so I can actually set the limits, right? You understand that? So I can set the current and I can set the limits. So my test circuit, before I hook up my power supply, before I hook up my, before I start building hundreds of these things, is going to be this. I'm going to come up here and I'm going to take a variable voltage supply that I can adjust between 7 and 6 volts. So this is going to be a variable supply. Now I can adjust this between what? 6 volts and 7 volts to verify my design. And then I'll come over here and I'll choose the RS. So RS is going to be 100 ohms. And what would the power rating on that be? So we take our maximum voltage, 1.9 squared divided by 100. Not the one you calculated, the one you chose. And what do we come up with? So y'all know by now a resistor is rated in more than ohms, right? What's the 3 things a resistor is rated in? Water intolerance and what power. So what would the wattage rating be? So we know it's going to drop a maximum of 1.9 volts. That's when it's conducting the most. Then we'll square that, and then we'll come up here and we divide that by 100 ohms. So I'm using a quarter watt. We could actually use an eighth of watt, quarter watt, because that's what we have. Okay. So then I chose my Zener. So I came over here and chose my Zener. Zener's going there reverse bias. Then I need some way where I can change a load. Instead of a random load, I can change a load. So I'm going to come up here and I'm going to put a 1 ohm resistor. And then I'm going to put a potentiometer wired to act like a rheostat. Now, of course, the 100 ohm resistor, so we'll call this RS, we'll call this R1, and we'll call this R2. First of all, why 100 ohm resistor? Because if I put this with this rheostat, I could adjust this thing all the way up here, which would put 0 ohms, and would short out my power supply, and it might burn up my resistor. So instead of my resistor dropping a maximum of 1.9 volts, it could be dropping a maximum of 7 volts. Everybody okay? This makes sense. And another thing nice about a 100 ohm resistor is when we set these currents, this is a 10K pot, is instead of trying to measure the current, I can measure the voltage drop across this resistor. And I can use it as a shunt, and I can calculate resistance. I can calculate current. So let's go ahead and do that. So plus or minus 5%, what should I measure right there? So I'll take 5.1 times 1.05, and I'll take 5.1 and multiply it by 0.95. Y'all understand what I'm doing? Plus or minus 5%, right? So what should be the maximum I measure right here? And the Zener still be within tolerance. 5.3 what? And then multiply it by 0.95, what should be the minimum that measures? About 4.8 something. 4.8. And these are both. Go ahead, Jim. That's the tolerance range. So this is, remember in DC what y'all had to do, you say, okay, I got a 100 ohm plus or minus 5%. And what y'all did was y'all took the 100 ohms and probably multiplied it by 0.05, and you came up with a number. Then you turn around and subtracted that number, and then you added that number to find out if the resistor, and then you measured the resistor, and you said if it was in tolerance or out of tolerance, right? Y'all remember doing that in DC? Well, what I've learned is I can come up here, and I can multiply by 0.05, and this gives me the upper tolerance, and I can come up here and multiply this by 0.95, and that saves one math operation, so I don't have to subtract. So 105, that's going to, so if you got a 10% resistor, then you multiply it by 1.1, and you multiply it by 0.8. And that would give you a 10%, right? That makes sense? So you can calculate these without trying to figure out, do an extra math step. So what we know is this is a 1N4733A. So that voltage might not be 5 volts, but it should, if we design this right, it should always be within that range. And if it's within that range, then this zinger's doing what it needs to do. 10K. And that's, I think that's what the design calls for. That's a K, sorry. So there's our circuit. Should be between 5.3, it should be between 5.35 and 4.84. If it's between that range, then this zinger's fine, right? You understand that? Calculated. It's cal is what it is. And these Zener power supplies will never use that resistance. That it'll give us a lot. It'll give us a starting point where we can come in. But what you're going to do is you always want the current to move away from that knee. So what we did is we calculated what resistor would put it right here. So if something happens and it goes up into here, then it goes out of regulation. So what we want to do is we want to put more Zener current in there, right? Understand? So this is our circuit. Oh. So it's hard to see the circuit. Here's my 100 ohm resistor. Here's RF. Here comes in my I'm connected up here to my plus 5 volt variable power supply. Now these power supplies are all referenced to this power. So if you use any of these power supplies, and these are referenced to this common. This transformer has the common is what you make it. And none of these power supplies are grounded, even though they call it ground. We proved that, right? We took our own meter, hooked it between the ground on the power plug, and measured that, and it measured infinite. So these are the unregulated power supplies. Here's my 100 ohm resistor, plus or minus 5%. Here's my Zener. Here's my common. Here's my load. So this is the 100 ohm right here that I've got my meter across, so we can measure the voltage drop and get the current. And then it comes back around and comes back over here to this common right here. So this is the circuit. So what we're going to do now is we're going to come up here and see if this thing is doing what it's supposed to do. I think the first part of the lab ask us if I got the lab up. Yes. So we chose, calculated the resistor, so that needs to be in that. From RS chosen, the maximum calculated voltage drop across the resistor. We did that, right? You'll understand that. From the calculations performed in procedure step 2 and 3, choose the correct resistor and the wattage rating. We did that. Huh? So we're all the way down to 5. Oh no, we're all the way down to 6 because the part number we chose was a 1N4733A. Are we okay? So here we're down to 6. Draw the circuit. So y'all need to draw the circuit. I'm going to do away with all these calculations. Which we did the last class anyway. So we can see the circuit a lot better. I'm going to leave that up there because we'll make sure that the zener is within plus or minus 5%. So there's our circle. By the way, these are quarter watts. Okay, so here's our circuit. So first thing I'm going to do is I think the next thing it calls for in the lab is for me to, where's the lab at? Draw the circuit, construct the circuit drawn in the procedure steps, connect the circuit using the trainer's positive power supply as the input, connect the output of the designed power supply to a 10 k ohm resistor wired in a series. Draw the complete circuit here. So what the first part, that's okay. First part we just draw the basic circuit. So the actual circuit, when it's in operation, it's going to look like this. It's going to be RS or whatever it is. You know, RS is generic, right? This is going to equal 100 ohms. Right here, this is going to be unregulated filters. So unregulated filter could be coming from a half-wave rectifier, Ozark Long. It could be coming from a full-wave center tap. It could be coming from a full-wave group. So that's the circuit right there. So that should be your first circuit. I'm sorry, we got to put a load. And this is where my load is going to change. What type of load is this designed to run? Well, it's designed to run any load that requires what? 5.5 around 5 volts at those currents that we specified. So when you design a power supply, that's what you need to do. What output voltage do you need? And what output voltage do you need? How much current does the load need? So when they designed these power supplies on this trainer, that's one thing they did. They designed these around 1 amp. So that's the maximum current. We don't know the minimum current, but they're 1 amp. Well, I do know the minimum current. Minimum current here would be 0. Because I can do what? I can disconnect the power supply. So right now, this 5 volt supply is running, is requiring 0 amps. So they had to do all that design, which would pick your transformer, which would come up and actually pick your capacitor. I've actually gave y'all the formula. We're not doing any of this, but on your formula sheet, I've gave you the formula on how to choose the capacitor to get the ripple voltage you want at the currents that we're specifying. So, and later on we'll add a bipolar transistor to this, and we'll have a really nice power supply. The problem is these guys, they're nice to use as a voltage reference, but they don't provide a lot of power. We can't get a lot of power out of these things. But I can get a lot of power out of a bipolar transistor, which is the next thing we're going to cover in class. So what I'm going to do is I'm going to come up here and I'm going to use, I got 2 meters hooked up. So this is the first circuit. This is the actual second circuit. I should have. So all I'm going to do is the yellow meter, both these meters turning stuff off. So this guy's going to measure, I'm going to use this. First I'm going to measure the input voltage, and I'm going to go over to the Zener voltage. So this is, wherever it's at. Right. So I'm not going to look at the circuit anymore. I'm going to move it up to the meter. And we might have to swap it. Yeah, now we can get it. So this is going to be the Zener voltage and the input voltage. This is the current. Let's go ahead and calculate that. So I've got a 100 ohm resistor right here. We're going to use this as our shunt. What a shunt is basically something you're going to measure from. Okay. So what we're trying to do is we're trying to get 2.5 milliamps, and we're trying to get 7 milliamps across a 100 ohm resistor. And I'm measuring voltage. V is equal to I times R. So V would be equal to 2.5 milli times 100 ohms. So this is the voltage we'll use to get across the 100 ohms for the 2.5 milli. And V, I should say R1, would be equal to 7 milli times 100 ohms. Do y'all understand that? Okay. Where did y'all learn all these formulas at? DC. Even calculating the resistor, we just had to figure out what voltage and what current we wanted. We're using Kirchhoff's law. So all these laws and everything you learn about DC, and that's what you're going to find out in this class. Most of the formulas we use, you learned in DC. We're just going to apply them. We're going to have to figure out, okay, what voltage are we going to use? What current am I going to use to calculate these, right? You understand that?
Question, where do we get the 2.5 milliamps?
That's the design parameter. So it says output load current varies between 2.5 milli and 7 milli. So what we're doing is we're using this resistor to set these currents. So if I'm going to adjust this pot right here until I measure whatever this. So what's this right here? 250 milli. Yeah, and this right here should be 700 milli. And that's millivolts, Rich. So when I get 250 millivolts across that resistor, and it's 100 ohms, that means I've got 2.5 milliamps of load current. When I get 700 millivolts across that resistor, that means I've got 7 milliamps of load current. This is what's nice about 101K. So we're okay. So now I know I can take my voltmeter. So let's switch over. So what's the first voltage we want to do? Zener part number. Draw the circuit. How the instructor check your circuit. Set the 10K to the mid-range. Adjust the trainer's power supply to set the input voltage to the minimum value given. Okay. So what we're going to do is let me switch back over to my calculator. I mean my camera. And we can see these pretty good now, right? So right now, my current flow is we'll set that in a minute. So I was supposed to set it in the mid-range, but we're okay. And I'm going to take my other meter lead as soon as I find it. Here it is. Here's my input voltage right here. And we need to set it to 6 volts. So I'm going to turn the adjustable thing on my power supply. Set this to as close to 6 as I can get. And let's see. then I'm gonna look at my Zener voltage, setting at 4.5 point, and that's within limits, right? Understand that? Everybody okay? Could have got down to what, 4.8 something? Okay, but wait a minute, we gotta set the current. What's the first current we want to set? Minimum current first. We're supposed to set this as a current. Using the measured calculated percent regulation of the power supply. So this is what we're gonna do. So we're gonna so these are what we're gonna do. V out when V in is minimum. Does it say where we're gonna mid-range? So let's set the positive. 4.9. We're still within limits, right? And then we're gonna adjust the input voltage between what? Right now we have 6 volts. So 6 volts, we got 4.9, 7 volts, 7 volts, we got 5.6. I mean 5.8, 5.1. We're okay? Everybody okay? Any questions so far? Okay, what's the next thing you tell me to do? So we want to measure V out with V in minimum and out of the load minimum. So 6 volts, 250 millivolts, right? Everybody okay? So here's 6 volts. Look, 6 volts. Yeah, this is the input voltage. This is 6 volts. Okay. Setting a load current to 250 milliamps, 250 millivolts, which is, we'll get as close as we can to the intake pod. Okay, I'll over that. And measure our Zener voltage. So we got an input voltage of 6 volts. We got a load current of 2.55, and then this is our Zener voltage. 4.97. Okay. Okay. Then let's go right. So this is still V in minimum. So we'll just go to the right. That way I won't have to readjust my input. And what I'm going to do is I'm going to bring my, I'm going to adjust my resistor so I can get 700 millivolts. 7 millivolts. Oh, I'm looking at this way. So here we go. Oh, I'll take that. So here's my Zener voltage at 700 milliamps, input minimum. My Zener voltage is 4.8. Okay, still good. Still looking good. Okay. Okay, so then we'll drop back to the bottom left. We'll do V in maximum, and we'll adjust the current back to the minimum. V in maximum. I'll come over here and set this minimum on it. This back to 6 volts. Okay, I'm happy with that. And then we'll set our load current back to 260. measure my Zener voltage. Oh my God. Okay. Oh, my input voltage. I noticed I had a problem right off the bat. I must have touched something. But right now, the Zener's out of regulation. But when I come up here and look at my input voltage, it's not 6 volts. It's supposed to be 7 volts. What's it supposed to be? Is it supposed to be maximum or minimum? Minimum, right?
It's the minimum, it's the maximum.
Okay. So this should be 7. That means we're going to have to redo our load current a little bit to get. Okay, 7 volts. I don't know what I did. And then I'll adjust it back down to. I'm happy with that. And here's our Zener voltage. 5.08. Then we'll leave the input at 7 volts, and now we'll go up to our maximum, right? We're okay. Am I ahead, anybody? I'll adjust this to get back up to 700 milliamps. 700 millivolts, which is 7 milliamps. Okay, I'm happy with that. Double check our input voltage. 7.02. Okay, so here's our thing. 5.02.
So the V out would be, V in is obviously going to be 7 volts that's coming in to the max. And the V out,
That's the output of the power supply, which is across the thing.
okay, so that would be the 5 volts right there.
Yeah. So what we did is we carried our power supply across the range that we designed it to handle, right? So what we need to do is figure out the percent regulation. So what is the Zener rated at? It's rated at what? 5.1 volts, right? What was the maximum voltage we got out?
Maximum, I think 504.
5.04. And what's the minimum we got out of our Zener? So this would be our percent regulation. What do we come up with? No, this is what we call the percent regulation. How close does it stay to what we designed it around? So we were designing it around 5.1. Which is what.
3.7.
So that means this thing regulates within 3.7% of 5.1. So what we did is we just calculated what we call the percent regulation. So you take what you shoot for, right? You understand, and then we subtract the difference. And that's not right. Sorry, let me go back and redo that. So this would be what we shoot for, so I need to, so this would be 5.1, and what was the minimum?
4.85.
And then we would calculate 5.1 minus the maximum. What's the maximum?
Maximum is 5.
And then we'll divide both these by 5.1. Sorry, guys. So what's the percentage right here?
I have 4.9. First one.
It's a point right there. So this is gonna regulate between here, right? That's my, meter saying it's fixing to turn itself off. Yeah, that would be percent regulation. Heard what Cameron said? Yeah. So that's it. That's allowed. Y'all got any questions?
Yeah, just one quick question. So then, you put we build the whole circuit on the train, and then the info goal is to use that voltage injector to take it up and down.
Yeah, it's to prove the rate, to prove what it is. It's just like, you know, if I was going to design an amplifier that was able to handle certain frequencies, and I come over here and look at audio looks like this, with this being your base. And it's all over the place. So instead of me trying to do with audio, I would get a function generator, and I would put a certain frequency into it, and I would measure the results. So I put knowns into my design instead of depending on true variables. You understand what I mean?
Yeah, so you got the pot is on that circuit train too, and that's what changes the current, right?
Well, yes, because it's a rheostat, and that's what we use a rheostat for. So what I'm doing is I'm changing the resistance of the load. If I change the resistance of the load and the voltage don't change, then it causes current, right?
Okay. So
But go ahead.
So what we did here is we did the voltage changer to change the input voltage, and we went over to the side and we used the rheostat to change the R2 current and the resistance to 250 to 700. Once we make that change, we go to minimum, then go to the center and check the center to see if it's within that tolerance.
Just say within tolerance.
Okay.
So we said we're going to design this so the actual full circuit. The actual full circuit. Once I put this thing into play, the actual full circuit would be this. Okay, so I set this design, and what I would do is, like I said, I'm gonna draw, instead of drawing a bridge, I'm gonna draw like I would come over here, this would come first, then I would come over here and I would calculate this capacitor to give me this thing that we just did, right? Understand? Now then we would take this, and this would be our circuit out here. So we're going to use a 100 ohm resistor, and it might be R10 in the actual circuit itself. And then we would have our Zener. And then over here, this is where we would connect our loads. But we know this load is going to vary between what? Between 2.5 milli and 7. And now we got our design.
Yeah, I think the only thing that kind of confused everybody was that rheostat changed that current.
Yeah, and that's what we're doing. So we're simulating a change in load.
Yeah.
But instead of this being arbitrary, like this circuit over here, I wanted to prove my design before I built my circuit. So I set up a static situation where I could actually put 7 volts in. I could actually put 6 volts in. Instead of the voltage over here on the input doing this. See? So this thing should regulate. If this maximum is 7, this is 6. This guy should regulate even though it's all over the place between 7 and 6, right? You understand that? So what we did is we put a static input on it so I could set 7 volts and do all my measurements, set 6 volts and do all my measurements, set 2.5 milliamps, set what? 7 milliamps. And once I prove my Zener circuit, then now I know it's designed. Now the design of a power supply always starts right here at the load. What load do you want your power supply to run? That starts the design of the whole thing. And then I've got to choose the right diodes. I got to choose the right resistors. I got to choose the right capacitors. I got to choose everything for this design. And like I said, I gave you the formula how to solve for C to calculate it for the currents that's required by the load. So you can take that formula sheet and you can design this power supply if you needed a power supply. The only problem with using a Zener by itself is that it can handle very low power. So our maximum power would be what? Power. Yeah, so the maximum, so let's just use 5.1. 5.1 times 2.5 milliamps, and 5.1 times 7 milliamps. That's what that's the wattage this guy can run. So Zeners by themselves are not designed to handle high power commands or high power demands. I know I said commands. But if I needed a real low power supply, then this right here would be great. If I need more power, then we're going to have to add other stuff to the Zener. We can use Zener as a reference, right? You understand that? But we can add devices that gives us a lot more current gain, gets us the high current gain. And we'll look at that too and show y'all, give you a good idea of how you could build a power supply pretty fast. And if we looked at the actual schematic of these 3 terminal regulators, then you'd find out that it's using a Zener as its reference. Somewhere in that schematic, it's going to use a Zener. But they're getting a lot more current gain out of other electronic devices. Right? And plus, circuits that sense when you overcurrent and undercurrent. So this is what the trainer uses. The trainer uses LM7805. Uses an LM79. No, I don't have a negative regulator. It uses a LM, or it might not be an LM. It depends on the company. These first designators, by the way, usually are the company. This is the indication of the company that makes the device. So if you saw a DM7805, that would be a 5-volt regulator, and it would meet the specs of a 5-volt regulator. And then we got a 7912. We have an LM7908. Oh, I'm sorry, 78. We have an LM78. One of those days. 7812. So the 78s, these are positive regulators. The 79, these are negative regulators. And we're using an LM317, which is a variable regulator, which is really neat. So all these connect like this. We come over here, we have our 3-terminal regulator, usually draw it as a block. We have a common, we have unregulated in, unregulated filtered in, and we have regulated out. And then, of course, it recommends that we come up here and put some pre-filters and post-filters in, but they give you the size. These are not your filter capacity. And we're through with the design. So if this had a 7805, then this right here would be a 5-volt regulator.
First, I want to apologize because I was lost when you were giving us the proper calculation. But I was wondering could we redo the VN and the minimum for the number 10, the V out for the VN minimum and current minimum.
There's no math involved. These are measurements.
We can just calculate that rather than.
No, we measured. Those are measurements.
I know, and I was kind of lost at that time. I'm so sorry.
Okay.
And from this one, just to kind of talk it out, if we're going to do that one, we would have to take the end and get the minimum to 6 volts, and the minimum for the load of the current would be 260 million.
Right.
We would both bring those down, and then we go to the end and
measure
see what that is. That would give us the answer for that.
Yeah.
Right? Yeah, when you were doing it, I didn't know where we were and what we were doing, and so we kind of came back and find that anyone else had the calculation?
The car V out, which is the Zener, that's the output of our power supply, right?
Yeah. So the V in this case would be 6 volts, you would have to change that to 6 volts.
Yeah, so we adjust this to 6 volts.
Yeah.
Then we'll set this for 250 millivolts, and this is V out right here. So this is V out right here. So V out is in parallel with the Zener. So you're measuring the Zener voltage, but we don't call it the Zener voltage. We call it the output of our power supply. Yeah, because that's the output of our power supply. So over here they say plus 5 volts. Now, what is that? That's V out. Well, how did we get that V out? Well, we don't know right now. Well, we do because we've already looked at the circuit. But,
do you remember what we got for that one?
No, y'all measured it. I mean, we could do it again. This is no big deal. So I'll come up here and don't keep saying that. So I'll come up here. My meter's powered off. Put this on volts. So here is our VN. So I'm going to come up here and set this for, right now we have it set at 7 volts. Why am I still measuring? Oh, okay, that's my output current. So I'll set this for 7 volts. Which is so that's 7 volts, so that's 7 volts in. And then I would set my load current.
Oh, it needs to be 6 volts, I'm sorry.
Okay. Yeah, you're right. And you want the minimum. Okay, that's good enough. And then we want the minimum current. So I'm going to come and set my plot to 250 millivolts. Okay. So it's close enough. Yeah. This might not come up exactly the same as before. Oh, that's cool. And then I measure my Zener voltage. This is my output voltage of my power supply. 4.97. And then 4.97. And and then we would go up to $700. I don't know how much up there, dude. Yeah, well, we're dealing with a 10K pod. It's like 250 degrees, and we're trying to set this very low voltage, so it's kind of
That's cool, so they had the little switch and you dial it down to 10.
a
425.
different thing. Maximum voltage. Open circuit. Maximum voltage, minimum current. 5.07. Maximum voltage. Maximum current. This is a 4,000 count meter, so the range is on 9399. So it's kind of looks good. Maximum voltage, minimum current. Maximum voltage, maximum current.
504.
Oh, yeah, cool. On these, they'll give you the recommended, what we call post filter, pre-filter, and post filter, but everything above this would be correct to here. Okay, any questions?